This lecture is going to discuss about ADC DAC, analog to digital conversion and digital to analog conversion that is going to happen during your digital communication process, and it covers your 15-minute topic, and it's very important for your digital communication process. Okay, before going to proceed in detail, first we'll see what is a signal. Signal is nothing but some information. It conveys some information, it carries some information, and it is a function of time and space. And the signals are processed by systems. A system is nothing but mathematical model which is used to perform something on input to obtain the desired result. And this process is nothing but digital signal. This process is nothing but signal processing. Okay, so the signal processing is nothing but applying something on the input system so that in order to obtain the desired output. Okay, there are different types of signals are available. Basically, our signals can be categorized into three different ways, that is continuous time signals, discrete time signals, and digital signals. So as the name implies, continuous time signal is nothing but if the given signal is continuous with respect to both in amplitude and time. A signal have the two types of information, that is amplitude, time and phase. If that signal is continuous with respect to both in amplitude and time, then it will be termed as continuous time signal. Then the next category is discrete time signal. As the name implies, the signal is which is continuous with respect to amplitude but is discretized with respect to time. That means the signal is taken at a discrete instance of time. It's not taken continuously with respect to time, it is taken at discrete instance of time. That's why this is called as discrete time signal. And the next one is digital signal. So with respect to discrete time signal, which is discrete with respect to time, digital signal which is discretized in both in magnitude and time, then such type of signal is digital signal. So here with respect to digital signal, the given signal is not taken continuously with respect to amplitude and with respect to time, and it is taken with respect as different is taken different with respect to amplitude and time. And it is basically a series of bits, and it is represented as 1 and 0, and these are the mostly signals used in your computer based applications. Then coming to the applications, we already seen the signal processing is nothing but applying on something on input and obtaining a desired output, and the process is nothing but signal processing. So then we'll see what are the different types of applications of signal processing. The signal processing will be used in different applications like speech processing, image processing, biomedical signal processing, communications, control applications and consumer applications, and robotics and radar and sonar applications. With respect to speech processing, basically it involves processing of the speech signals. Okay, so which is nothing but recognizing of the given speech signal, or it may be speech enhancement, or it may be synthesis of the given speech signal like production and suppression, or it may be mixing of the signal with another signal. With respect to image processing, the image processing involves like image enhancement, image recognition, image compression. With respect to medical side, there is a processing of the biomedical signals like heart signal with respect to electrocardiograph signals and electroencephalography signals, like that is EEG signals. Coming to the communication processing, it is like processing of the telephone signals with respect to internet access, and during the fax processing. During all this communication, you will be using signal processing. And with respect to consumer side, you have so many digital components are like digital TV, digital cameras and mobile phones, and different types of digital toys. All these type of consumer side applications, you will be using your signal processing. Next we will see what are the different ways of your signal processing. Signal can be processed in two ways, that is analog signal processing and digital signal processing. In analog signal processing, with respect to the signal processing system, both the input and output signals are in analog form. With respect to digital signal processing, both input and output signals are in digital form. We are going to see this digital signal processing in this lecture. Yeah. So digital signal processing, we already discussed that the input and output should be in a digital form, and it is used mostly in digitalized processing applications like your computers, modems, and digital communication applications. So, and this is a block diagram of the digital signal processing. If you notice over here, this is a digital signal processing component. Mostly here you are going to use a digital processor like your computer or mobile phones or modems, etc. So, but anyway, even though you have the digital signal processing component, but the signal that need to be given for this digital signal processing component should be digital form. Whereas we'll be having analog signal as the input. So, in order to give this digital input as digital input for this digital signal processing, you need one converter, that is analog to digital converter. Similarly, once you have the output as digital from this digital signal processing, so in order to process that signal, it is given to the other side of the analog signal component, the signal again should be converted back into the digital form, in analog form. So we need another converter, that is digital to analog converter. Basically, this digital signal processing needs one digital processor and one A-to-D converter and one D-to-A converter in order to process the signal in digital signal processing. Well, we'll see one of the application. So this is one of the simple examples with respect to digital communication. Here, if you notice here, two different types of digital components are there. So this is one type of deep space communication, and it is one type of point-to-point communication between the Earth station and the robot that is there on the surface of the distant planet. So here actually this big antenna is going to send some computerized signals to this robot, and this robot, it is going to be taking those signals, and those signals will be analyzed in such a way in order to measure the soil content over this planet, and the results will be sending back to this Earth station. So basically these two are at different places. That means it's a very large distance, and basically in order to cover these two components through physical media, it is impossible. So in such scenario, we can go for the digital communication. Basically, by just replacing these two medias with respect to digital communication media, we can able to communicate at the station with respect to the robot that is there and at distant planet. So here this digital communication will be replaced like your digital signal processor, A-to-D converter and D-to-A converter. And whatever the signal that is coming from here will be taken by this digital communication component. This will be given as the output to this robot. So this robot will take the signal and it will analyze this, and it will produce the output again, send it back to the digital communication. So this digital communication, after taking this one, it will convert them back into the analog signal form, then that will be given to your Earth station. So this is one of the scenario with respect to the digital communication. Next. So we'll see how this analog signal is going to be converted into the digital signal. In order to convert this analog signal to the digital signal, we have three operations, that is sampling, quantization and coding. Yes, sampling is nothing but converting the continuous signal into the discrete time signal. So that means continuous time signal, which is continuous with respect to time and amplitude, you are going to convert it into the continuous with respect to amplitude but discretized with respect to time. That means you are going to take only the discrete instance of the samples of the given signal. That means you are not taking the entire signal, you will be taking only the some instance of the time signal of the continuous time signal. And this sampling, that means at which instant I have to take the input of the continuous signal will be decided by the intervals of time. This intervals of time is called as sampling rate. Okay, and this process is nothing but sampling. The process of converting from the continuous time signal to the discrete time signal is termed as sampling, and the time interval, that is which is needed to take at which instance of time my continuous signal to be analyzed will be decided based on the sampling rate. And the sampling rate mostly will be taken as 2 times the maximum frequency of the input signal. and this is called as Nyquist rate. Why we are going for taking the 2 times of maximum frequency? That means once the signal is converted into discrete time signal, to retrieve back it to the continuous time signal, we have to take this rate. So as this this rate is decided by Nyquist, so it is termed as Nyquist rate. Clear? So here actually your sampling is nothing but converting the continuous signal into the discrete time signal. That means you are going to converting the continuous time and amplitude signal into the continuous in amplitude with discretized time input signal. That means basically here you are going to take the samples of the continuous time signal at different instance of time. At what instance, that will be decided based on this sampling rate. And what is this sampling rate is? It is equal to 2 times of the maximum frequency component, and this is called as Nyquist rate. So this is what your continuous time. This is what your sampling process. So this is explained with respect to an example. So basically this is your continuous time signal x of t, and this will be multiplied with this impulse time. This is nothing but p of t. This impulse time will decide at which instance of time my input signal to be sampled. And this is what the t. This t is nothing but your sampling rate. That what we discussed in previous slide. Okay, this will decide at which instance of time my input signal to be sampled, or the input of the input signal to be taken. Okay, so after multiplying this signal component with respect to this signal component, this is the sample signal you are going to have. That means you don't have the continuous, you have the continuous with respect to amplitude, but you are not taking the continuous values of your time signal. You are taking only the discrete instance of time. So this is what you are the sampling signal. Okay, so the same example is given elaborately over here. So this is a continuous time signal, and this is past, and this is the impulse train. So impulse train, and these two are multiplied each other. So at this instant, what is the value of that? That will be taken as one sample. At this instant, what is the value? That will be taken as another sample. And at this instant, what is the value? These two are multiplied. That will be taken as sampled value over here. So this is what the conversion from continuous time signal with respect to the discrete time signal through the process of sampling. Next, so sampling process is over. Next one is quantization. So quantization is nothing but basically here we sample the signal with respect to the time. Similarly, you have to do the sampling with respect to the quantization. That means you are going to dividing the amplitude into different levels. So you are going to divide the amplitude into different levels, and this process is nothing but quantization. So to how many levels I have to split my amplitude, that is decided based on the way that you are going to represent each amplitude. That means if I am going to represent the amplitude as a 4-bit pattern, then you will have the 2 to the power of 4, that is 16 levels you can represent the amplitude of the signal. Okay, so after dividing the amplitude to what is the value of that corresponding amplitude, that you will be rounding up to the nearest level of the selected amplitude level. Okay, so after performing this quantization, we will have the given continuous signal will become discretized in both in time and amplitude. So the process of discretizing the discrete time signal with respect to the amplitude is nothing but quantization. Basically, in this quantization, you are going to dividing the amplitude into different levels. What are the different levels I have different? That is decided based on the bit pattern that you are going to using for that signal. If I am going to using it as a 4-bit pattern, so the quantization will be divided into 2 power 4 is equal to 16 levels of data. Then that 16 levels of data, each corresponding amplitude will be rounding to the nearest value of the corresponding level amplitude. So after quantization, you have the signal of the signal input. The continuous signal will become discretized in both in time and amplitude. For example, if I am going to use my bit pattern for representing the amplitude is 16-bit means, then I can able to represent the amplitude nearly to the 2 power 16 levels of amplitudes. So that is about the quantization. Now we'll see the example based on this. Yeah, see here. So this is the continuous time signal actually. So this is discretized with respect to time. So this grid will represent the discretization with respect to time. And similarly here in the amplitude also the signal is divided into different values. So if you notice over here, so this is our continuous signal. So here this value will be given to the nearest amplitude of this level. Similarly here another sample you are taking is at this instant, and this value will be given to the value of this thing. And similarly this is another value you are going to take your continuous time signal, and this value will be taken as to this nearest value. And similarly here also this you are going to be taken to the corresponding nearest value. Like that all your continuous values of the amplitude will be taken to the nearest amplitude values based on this discrete value of the time. So this is what your quantization process. Next, coding. So the digital signal is nothing but which is you are going to represent the values in zeros and ones. Okay. So now we have seen representation of the amplitude and representation of the time. So this value how should I represent? Okay. So here actually this grid you are going to represent with respect to 8 different values. That means you have 8 different amplitude levels. 8 is nothing but you can represent each amplitude with respect to 3-bit pattern. Okay, so this is your lower level. So I am taking that lower level as 0 0, and next level as 0 0 and 1, and next level as 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 1, and 1 1 1. Okay, so totally 7 values. So when I am sending after the quantization, how should I send to my computer? I am going to sending the signal in terms of the distance. Distance is nothing but you have the square waveform which is having low and high. Okay, so that low and high you are going to represent by after the coding process. That means so here you will have so here the amplitude value is 0 0. So you will be sending the signal as all low levels. And coming to here, this the value of this amplitude is, and it is near to the somewhere 0 1 1. So this value will be sending as 0 1 1. And here this value is near to your somewhere 1 0 1. So this you will be sending as high, low, high. Similarly here this value you are going to represent as 0 1 1. So this you will be sending as a low, high, high. So like this after coding you are going to sending the continuous signal as a one digital signal which represents the zeros and ones. Okay, so that is what about the analog to digital conversion. So if you notice over here we covered what is sampling process and quantization and coding. So sampling is nothing but converting the continuous time signal in terms of the discrete time signal. That means we will be taking the discrete instance of the continuous time signal. Similarly quantization is nothing but you are dividing the amplitude into different levels based on the bit pattern that you are going to use. And coding is nothing but representing those amplitude in terms of the zeros and ones. And those zeros and ones will be sending like a square waveform to your digital medium. Okay. So next we will see about digital to analog conversion. Before going to the digital to analog conversion, first we should know what is the filtering actually, because once the signal is transferred through the media, it may be affected by so many noises. So we should avoid unnecessary components in the signal component. So we should know what is this filtering and all. That means you have to avoid unnecessary signal. So filtering you already know, you will be knowing, already come across with many terminologies. Filtering is nothing but avoiding unnecessary signal from the input signal. Why this is happening? Because you are sending the signal through different wires and different components. So there may be some of the free unnecessary components will be added to the signal component. So we have to filter, we have to cut those components. That cutting of the unnecessary signal is nothing but filtering. Basically there are two types of filtering. There are basically two types of filtering. One is ideal filtering and another one is real filters. We will see one by one. Yeah. So ideal filter is nothing but with respect to ideal is nothing but, so this is like it's like a some square waveform representation. There are basically four types of ideal filters: low pass filter, high pass filter, band pass filter and band stop filters. Based on the way the component that you are going to be cut from the input signal, these ideal filters will be categorized into four: low pass filter, high pass, band pass and band stop. So coming to the low pass filter, see the diagram representation. See, it is like a, so it is a square waveform. That means this part of signal only it is going to cover, and it is going to cut this side of the component. So highest frequency component it is going to cut, it is going to cover only the signal that is going to cover in this region. Similarly, high pass filter is nothing, basically it is for edge and transition detections. So edge and transition detections. So it is going to cover only the high frequency components, and it is going to cut the middle lower frequency component. This is just reverse to your low pass filter. So in high pass filter, we are going to cover the component which is under this cap, whereas in this high pass filter, you will be covering outside of these caps. It is going to cut this part. And band pass filter, it is going to cover two different regions, that means region 1 and region 2. So these two bands it is going to cover this during this band pass. That means it will use the remaining components where it includes only this component. That means sometimes I may not want in this type of component. Sometimes I want only in some band of frequency, that you will have to go for band pass filter. Band stop is just reverse of your band pass filter. So it is going to cover the cap in between this one, and it is going to cut the region from this part to this part and this part to this. So it is just reverse to the ideal filters. But anyway, in general, we won't have this type of filters because of the capacitors and because of the inductance. We won't have the exact filtering component like as low pass filters. That's why we'll go for the real type of filters. With respect to the real type of filters, so the signal representation of the low pass filter is like this. It is not the exact the square wave shape. It is something like deviation from the square wave. Okay, so you will be obtaining in real time. You will have this type of filters only, and your high pass filter also not exactly like your square waves that you have seen in the previous slide. This is something like the frequency component which is curved with respect to the middle. Similarly, here also the curve shape also. Here also you have the curve over in the cap sets. Okay. See the example here. This is a signal I am going to use. I am going to pass this one through this low pass filter. So in this low pass filter, what exactly it is doing? It is going to cover this component, and it is going to cutting the higher frequency component. That means the component which is under this cap alone, it is going to cover, and remaining times it will cut. That's what your low pass filtering. Similar with respect to high pass filtering, you have the component which is the highest frequency. It is going to cover only the highest frequency component, that is during a edge and transition detection of the signals. That is, it is going to cut this component. It is able to check only the higher frequency components. Okay, one of the example of the filtering is, see here, this is my input signal. So because of the some wiring technique, when I am passing this input signal through media, I have this filtering component is added. So when I am passing this component through my wires, what happened? This signal is added along with noise. So in order to obtain my signal over back, what I have to do? Actually, I have to cut these lower side components, because this is an extra component added with respect to my low pass with respect to my noise component. So I have to cut this component. So when I want only this component, I don't want this component, obviously you have to go for low pass filter component. So after passing that resultant signal of this X of f and N of f, you will be getting the y of f, which is a desired form of your x of f. So your here x of f is your input signal, and n of f is the noise signal that is added through the components. So after once this signal is passed through these components, this signal is added with the noise, and this noise I have to cut down. So in order to cut this one, I have to cut this part only. So in order to cut that one, I have used over here low pass filter. After the low pass filter, this signal became as usual like your input. Yeah. So now we will see this digital to analog conversion. In previous case, we have seen analog to digital conversion. So in analog conversion, we have the process sampling, quantization, and coding. So coming to this digital to analog conversion, basically it is nothing but reconstruction of this signal. That means in previous ADC, what you did, you have taken the analog signal and you converted into discrete time signal or digital signal. But here that reconstruction is nothing but you will be having the digital signal and you have to convert back your analog signal. Because for example, when I am sending the speak signal to your speakers, the speakers can able to understand the analog form only. It won't understand the digital format. So in such scenario, obviously you have to convert those converted digital signal into the speakers recognized analog signal component. So basically digital to analog conversion is nothing but reconstruction of the signals, and it indirectly involves the connecting of the sample. That means basically in analog to digital conversion, we have taken the samples of the input signal. So here in reconstruction is nothing but we are going to connecting those samples, and this connecting of the sample is termed as interpolation method. So this method is called as interpolation method. Basically it involves reconstruction of the signal. Reconstruction of the signal is nothing but connecting of the samples, and this connecting of the sample is termed as interpolation method. Yeah. So there are basically three types of interpolation methods, that is band limited or ideal interpolation, zero order hold, and first order hold. So by the way how these samples are reconstructed, based on that the method is divided into three different ways: band limited, and or ideal interpolation. In this band limited or ideal interpolation, you are going to use ideal filters in order to construct your signals back to the analog form. Wherein in a zero order hold and first order hold, how the two amples are get connected, based on that those two type of methods this will be taken place. Now we'll see the first method, that is band limited or ideal sampleized form. So if you notice, so this is your input signal and this is the sample signal after sampling, and this is the signal after quantization. So with respect to the ideal interpolation, here you are going to passing one ideal low pass filter over here. So when you are passing this signal over through here, so this is a resultant signal you are having. So you cannot able to recognize this is a mixing of the different sync function. So this is not the correct representation of giving your original signal. So we'll go for the next method, that is zero order hold interpolation. So actually here this is two samples are connected through each other through one step function. That means the converts its digital signal to the convert signal by holding each sample value of the current sample value till to the next sample value. For example, here this is the sample value I am having, and next sample value I am going to have over here. Still this time I am going to continue this same signal. So when I am having this instant, I am having the sample value as this one. So these two are connected by one step function. Similarly here this is my sample value and this is my next sample value. Till to the next sample value I am maintaining the same value, and after that I am just maintaining one step, and here is my sample value over this instant, and till to the next level I am maintaining the same level, and actually this is my sample, so I am connected. So each two different levels are connected through one step level. That is what your zero order interpolation. That means two sample values are maintained one step levels of input. So this is the exact sine wave function, but after interpolation, this is the way you will be obtaining your signal. So this is almost similar to your original signal, whichever you have given. But anyway, still it is not giving the exact signal of your input signal. So we'll go for the next method. It is first order hold. It's also termed as linear interpolation. Basically, here the two samples of the given signals are connected through straight line. Instead of a step function, here I am going to connecting these two samples by using a straight lines. So that is what happening over here. So this is the sample 1 and this is the sample 2. This I am going to connect it through straight line like this. Okay, so this straight line, and from here to here again one straight line like this, and from here to here another one more straight line, and from here to here another more straight line. Like this the waveform will be reconstructed with respect to the first order hold. Clear? So in first order hold, two samples are connected through straight lines. In zero order hold, two samples are connected through some step function. So if you notice in both cases, actually which one you feel more better? So we feel this first order hold is more better because it is giving exact exact representation of the given input signal compared to your previous things. So here it is not giving exact representation of your input signal. Even in band limited signal also the signals are interlinked with respect to different types of sync functions. Okay, so if you comparing all these things, so the first order hold interpolation is more better than compared to your zero order hold and then band limited interpolation. Okay, so then coming to the frequency representation of all three things. So this is the representation for band limited ideal interpolation filter, and this is a representation with respect to zero order hold, and this is with respect to first order hold. Okay. Okay, so still more you can have the second order hold. So this will give still more curving part. So if you notice over here, this is little bit curved part with respect to this ideal sample filter. So that's why it is more better than this ideal interpolation filter. If you notice first order, it is still more curvy than zero order hold. So that is you will obtain more approximate signal with respect to the input signal. So if I am going for still second order filter, I can have still more curvy of the input signal. So like that you can have the different types of interpolation process. So this basically covers this DAC conversion. So in DAC conversion we have interpolation method. We have the ideal interpolation filter, zero order hold and first order hold. So in ideal interpolation filter, you have the filter that is low pass filter you will be using, and in zero order hold, two sample waves will be maintained through one step function. In first order hold, you will be having the straight line between the two samples. So this is what about your ADC and DAC conversion. Thank you very much. Check. 1, 2, 3. Hello. 1, 2, 3. 1, 2, 3. Good morning, students. I am going to discuss about DAC and ADC.